So Newton's third law on the surface is actually a fairly simple law. It essentially states that for every force, there is an equal and opposite force. Okay? And mathematically, that would mean if I apply a force, there is another force that is the exact same size, but it's going to be equal and opposite. And essentially what that means is if you have a wall, so this is my wall, and I push on that wall with a force of 10 newtons, that wall is exerting a force back on you of minus 10 newtons. So basically it says if something pushes on you, something pushes back on you with the exact same force. But that also means since force is mass times acceleration, then the mass of one object times the acceleration of that object must also equal minus the mass of a second object times the acceleration of that second object. Okay? So this on the surface is a pretty easy law. Now, when we deal with Newton's second law, or third law, excuse me, there are always two forces involved. An action force, okay, which is the one that starts the reaction out, and then the reaction force. So there's always two essentially forces involved in this law, an action force and a reaction force. So as an example, okay, if you're just walking on the floor, okay, we cannot walk on the floor without Newton's third law. Essentially, when you walk on the floor, you push on the floor, okay, with your foot, and then the floor pushes back on you. So if you were to write Newton's third law out this way, it basically says there's a force of U on the floor, and that must equal minus the force of the floor back on you. Okay? So there's always equal and opposite forces. So I have some pictures here, okay, where we can maybe identify the action and reaction forces. Okay, this first picture right here, a guy shooting a gun, okay, there is a force of the gun on the person, okay, and that must equal minus the force of the person on the gun. Okay, so those forces would be right in there. The gun is going to exert a force, and the person is going to exert a force. Okay, here's another one. Okay, where you're swinging a bat at a ball. Okay, so there is a force of the ball that is on the bat, and that must equal minus the force of the bat on the ball. So there's the ball on the bat and the bat on the ball. They are equal and opposite. And one last real quick picture here. Okay, this catcher that's catching this ball, there's a force of the ball on the glove and the force of the glove on the ball. So there's the force of the ball on glove equals minus the force of the glove on the ball. Okay? So, I want you to draw this picture in your notebook. And this picture has 6 action and reaction forces. So before I identify them, I want you to pause the video, draw the picture, and I want you to identify the 6 action and reaction forces. So now I'm going to identify those for you. Okay, the first ones are kind of easy. There's one right here where there's the force of the tractor on the rope and the rope on the tractor. There's one right here, okay, where there's the force of the guy on the rope and the rope on the guy. There's another one here, same force, and then there's another one here. So those are 4 obvious forces. Okay, The forces that usually get missed are right here. There is a force of the tractor on the ground, and that must equal minus the force of the ground on the tractor. Okay? And therefore the other one is right there, the force of the elephant on the ground and the ground on the elephant. Okay? So now, one of the things that comes into play is if you kick a football, and if forces are equal and opposite, how does the football actually move? Okay? Because you're going to sit here, okay, there's my football, you're going to come in and you're going to kick the football with your foot. So, there are equal and opposite forces here. There's the force of your foot on the ball and the ball on your foot. And if those are equal and opposite, so let me write that out. There's a force of your foot on the ball, and that must equal minus the force of the ball on your foot. And the question becomes, how does the ball actually move then? Well, there's two answers to this actually. One of them is because the forces are actually acting on two different objects. Okay? The forces are not acting on the same object. So it's not like two people are kicking the ball from opposite sides. This would be two forces on the ball, okay, and the ball wouldn't move in that case. So the forces are acting on two different objects. But the other thing is the masses and accelerations are different. Okay, if I go back to the original equation, force equals minus force, and understand that force is mass times acceleration, then what you also have here is the mass of the foot is pretty big. Okay, I'll put mass of foot here. But the acceleration of the foot is going to be small. But that's also going to equal the minus the mass of the ball, which is small, times the acceleration of the ball, which is actually going to be much larger. So masses and accelerations can also be different. Okay, so I have a kind of a better example here. So if you were to drop a ball on Earth, okay, essentially the forces that are attracting the ball to the Earth, so there is a force of the ball on the Earth, okay, and that actually has to be equal and opposite to the force of the Earth on the ball. So technically, if those forces are equal and opposite, then what should happen is they should meet in the middle. Okay? So as the ball falls to the Earth should come up and meet the ball. They should meet in the middle. Well, we know from all of our experiences that that doesn't happen. We know that the ball just goes and bounces on the Earth's surface. Okay? So again, they are equal and opposite. So the force of the ball on Earth does equal minus the force of the Earth on the ball. Okay, but if we go with F equals ma, okay, the mass of the ball is itty bitty. Okay, the mass of the Earth is huge. So what happens is the acceleration of the ball is huge compared to the acceleration of the Earth. Okay, and that's how they can be equal and opposite. Okay, so that goes back to this statement that I made right here, that masses and accelerations can be different. Okay, and I think that's pretty much all we need.